Hello, I'm Tomer. So I'm going to talk today about a real project that we had in PyData, and it deals with zero inflated continuous regression. Just a few words about us. So about me, more than 4 years in PyData, a lot of experience in financial markets, algo trading. I guess you will be surprised how much doing analysis in financial markets can be fruitful in working with behavioral analysis, just a comment, and pure mathematics background. And our team, so basically I work in a House of Fun, which is one of the studios in PyData. PyData is built in as a number of studios. So we are a team of 5 data scientists and offering solutions to nearly all departments, including product, marketing, economy, VIP. And we are working closely with data engineering, of course, the BI, BA, DevOps. Some of the tools that we are using are indicated there. Suppose we want to predict some numerical value in which we know that has a very specific shape. This is what we call a zero inflated shape. So you have a mass probability in 0, and other values are positive values. So we cannot really change or transform this distribution into something that looks more of a Gaussian. So what could we do? Specific examples that we faced dealing with this problem. So let's assume that we want to predict the total deposits of a user. So we know that we are in PyData, we are a freemium game, so most of the players are not deposit-on players. So some examples of test cases is, for example, marketing campaigns. We are spending a lot of money on campaigns to bring new players to our app. And we would like to be able to say about campaigns whether they are good or not. So good can be regarded as linked to engagement, but of course we are interested in revenues. So we would like to know whether a campaign is good, meaning that we will see revenue for such a campaign or not. So maybe we can terminate a campaign, stop a campaign, or maybe even enhance and get it to run a longer time. Another aspect is for our VIP users. So we have our VIP managers dealing with those users. They would like to know whether some of the users will have some regression in their depositing patterns. So this is very important. So what we can do, we're trying to tackle this issue. So we can go plain regression, like deep architecture, maybe some boosting. We can use 2-step models. So we can try and classify at the first step who are the users that are going to pay, and run a regression model on those positively predicted users. So we know, and the data supports that we have a major imbalance issue with data. So this classification can be quite challenging, not speaking of on the regression that will follow. Just a comment, so Moshe will talk about imbalance using deep and geometrical methods, autoencoder and stuff, so stay tuned. We can try even predict the number of future transactions using something like Poisson regression. And then once having a prediction for the number of such transactions, just multiply this by something that characterizes the user's specific transaction, like median, average, some weighted moving average, or something like that. Maybe we can go Bayesian, having a prior on the output, maybe we can use that. Or some other deep architecture. We have work in progress dealing with multitask neural networks. So still in progress. So what we want to discuss today is the 3D distribution. 3D distribution, it has, as you see, it shares the following characteristics. We have a linkage between the variance and the expectation given in this formula. And actually 3D distribution is a generalization of more known distributions like the Gaussian, the Poisson, the Gamma, Poisson and Gamma you see here. Poisson and Gamma. And this is dictated by the P, which is the power that is implied to the expected value. There are other values, 3 and more, that relates to a more esoteric or less known, but we are mainly concerned with the compound person, Gamma, which deals with the power which is in the range of 1 and 2. So having the P in the range of 1 and 2, we get the compound Poisson Gamma distribution. So this is actually nice. It's like having a random variable which you can present as a sum of a specific number of gamma random variables, but the number of such gamma random variables is dictated by a Poisson. So assuming we are dealing with deposits, we can have the T there being given by a result of a Poisson distribution. And once we have the number of transactions, which is T, every such transaction can be represented as a gamma distributed. We have several connections between the parameters given here. Now, as we have seen, the P kind of controls the shape of this distribution, as you see here. So you can get sometimes very crazy such shapes of distribution. For example, this one. This is more of a Poisson. Like we mentioned, the P is equal to 1. Also, we have another parameter, which is the dispersion that controls the shape here. It relates to more of a variance, as you see. Now, the thing is the question is whether we know, if we know something about the target distribution, whether this can help with the prediction. So we know that we are running some deep architectures to deal with regressions, but here we actually know something which is very special about the target distribution and its shape. So we want to be able to apply some model that can deal with this distribution. So actually this area of using this distribution came from actuary, from insurance, predicting the number and the absolute value of claims. So this is like one of the resources of those academic work that was done. One implementation is due to these guys that they have built tree boosted algorithm. The difference between, or we can say the addition that we have in this algorithm is the loss function that takes into account the likelihood of this special distribution. So just to present one test case in which we have applied this model. So we wanted to predict the next 30 days total revenues for users. And those are already depositor users. So we did not try to predict whether they will convert, they will deposit for the first time. We know that substantial number of such users will not deposit. So this is why we use the 2D regression, and we have in this model several dozen of features. Some relate to logins, engagement, some relates to deposits, plane activity, all sorts of features that we have extracted. And additional guidelines to the model. We try to help the model in part by pre-segmenting our population into 5 parts. The reason for that is to have our models running on more homogeneous set of users. Each of the groups also shared this 2D distribution, so it makes things much friendlier. And we were running different models for different segments, of course. So we took the XGBoost linear regression as a baseline. So we all know that XGBoost usually gives us good results, sometimes even very good results. So the competing model was XGBoost, but using the 2D as the distribution. So the goal was to see whether having a prior knowledge on the distribution can make a difference. So moving to the model performance, first just to the aggregated evaluation metrics, we have the mean absolute error and the root mean square error, mean average error or deviation. So we just see that on aggregated level, the 2D did better. So maybe not, we see like 90%, but in any case, it did better on an aggregated level. One thing which is important to notice is that the difference between the 0% or the a proportion of zeros in each of those groups. So we see that it can range for nearly 95% in group A to somewhere within the 10% in group E. If we move to a finer analysis of the results, we would like to see, so first we have the predicted minus actual divided by the actual. This is like the error, but not an absolute value of the error, divided by the actual. We would like to have this value equal to 0 to say that we have an ideal model. So what you see here, this is like the 0 line. And again, we would like to have all the predictions giving us 0, but of course this is in ideal world. So we have the 2D in green and the regular in red. We see that in group A, which suffers from the most severe imbalance issue, that the 2D is doing much better. And as we go along those groups in which we have seen that the 0 proportion gets to be either maybe negligible, we see that the difference is very minor, if at all. So we see the effect of the 2D regression, knowing that the distribution requires something like the 2D. I didn't mention that, but here, of course, I cannot really divide by actual for all the users. I only divided that for the users that got positive predicted values. Sorry, positive actual values. So what about those users that had actual 0 values? We mentioned that the 2D should handle that. So as we see it, we would like to see that knowing that user did not deposit, the model should reflect that. And this is what we see here, having the ratio of the 2D predictions and the regular predictions, and we have this ratio which is less than 1 in all the cases, but significantly small for the group with very small number of positive values. So it handles this in a very good way. So to conclude, if we want to predict zero inflated target, knowing that can help by using this 2D regression or other distribution. The more zeros in output, the greater 2D regression's effect. So it really shines when we have more zeros. Now, using boosting methods is something that it is very common nowadays, and we were only running the P parameter as one of the parameters, but all the other parameters were optimized using any other way you know, whether this is Bayesian or other. Some implementations that exist are, of course, the XGBoost, the non-XGBoost. We have H2O that allows you to use GLMs as well as deep, dense networks with the 3D distribution. We have LightGBM. We have several packages for R and Python, and Spark also allows you to run GLM models using the 3D distribution. So working we are now working on different architecture of deep neural networks, still work in progress. That's it.